Hi, in this lecture we will see about Gauss Divergence Theorem. So we will see a problem. Verify Gauss Divergence Theorem for f vector equal to 4xz I vector minus y square j vector plus yz k vector, where S is the surface of the cube formed by x equal to 0, x equal to 1, y equal to 0, y equal to 1 and z equal to 0, z equal to 1. And we know that Gauss Divergence Theorem is double integral over the surface f vector dot n cap ds equal to triple integral over v del dot f vector dv. So here we are integrating the surface integral and here we are integrating the volume integral. So we have to verify both these sides are same. So the given vector is 4xz I vector minus y square j vector plus yz k vector, and we have a cube picture here. So here you have x, y and z plane. So we have formed a cube. So you can see this yellow region which is S1 is the surface S1 which is in the xy plane, and parallel to xy plane you have S2 that is also made in yellow color, you can see that. And now you can see the other regions. S3 is this xz plane and S4 is parallel to xz plane. Similarly, you can see in yz plane S5 that is in green color, again that is inside this, that is just fixed in the wall, for example. So you can see that is your S5, and S6 is nothing but the view of the other side that is parallel to yz plane. So that is your S6. And now you can see the unit outward drawn normal drawn with S1 which is in downward direction. So in xy plane, which variable is missing here, which plane is missing, z is missing. So z corresponding vector is k vector. So here you have n cap is minus k vector, and parallel to that, so here it is in the top, so it goes outside, so outward direction, so n cap is k vector. And you can see here in xz plane S3 you have which is towards the inner side, so n cap is minus j vector, and S4 which is parallel to xz plane which is n cap is j vector. S5 you can see n cap is minus I vector because it is going inside, and S6 which is coming outside, so n cap is plus I vector. And of course this cube is drawn with 1 centimeter in all the sides x, y, z. So based on this picture we will try to formulate our integrals here. So let us verify this side, triple integral over v del dot f vector dv. So the right hand side we will take here. So we need to evaluate this integral, triple integral over v del dot f vector dv. So del dot f vector, what is del? I dou by dou x plus j dou by dou y plus k dou by dou z dot f vector is the given question, 4x is I vector minus y square j vector plus y is k vector. Now you can very well see this is the dot product, so I dot I becomes 1, j dot j becomes 1 and k dot k becomes 1, the remaining dot products are 0. So when I dot I becomes 1, this dou by dou x is multiplied with 4xz. Similarly, when j dot j becomes 1, dou by dou y is multiplied with minus y square. And when k dot k becomes 1, dou by dou z is multiplied with yz. So you have dou by dou x of 4xz when you differentiate this with respect to x, which is 4z, and dou by dou y of minus y square when you differentiate, that is minus 2y, and dou by dou z of yz when you differentiate, that is plus y. So 4z minus 2y plus y, minus 2y plus y becomes minus y. So 4z minus y is your divergence of f vector, that is del dot f vector. And also the limits are given as x equal to 0 to 1, y equal to 0 to 1, and z equal to 0 to 1. So we just apply that here. So here you can apply in any way this limits, because these limits are constants. So you can apply x equal to 0 to 1, and then like z equal to 0 to 1 or y equal to 0 to 1, like that. So in any way you can do. So that theorem name is called as Fibonacci theorem. Okay. So whenever the limits are constants, you can apply in any way, right? So you do that, then you can just substitute the del dot f vector here. You're substituting in this place, and dv is of course your dx dy dz. So when you integrate, so with respect to the x integration, 4zx minus yx. So the limits are 0 to 1. So when you apply 1 here, it is 4z minus y, and lower limit is 0, of course. So you get like this. Then again, when you integrate with respect to y, you get 4zy minus y square by 2. So that is shown here. Okay, 4zy minus y square by 2. The limits are 0 to 1. So you apply for y 1 here. So 4z minus 1 square is 1 by 2. So you get 4z minus 1 by 2. Again, when you integrate with respect to z, you get 4z square by 2 minus half into z, that is z by 2. Limits are 0 to 1. Again, you apply the upper limit, which is 4 into 1 square is 4 by 2 minus 1 by 2. Lower limit is of course 0. So 4 by 2 minus 1 by 2 is 3 by 2. So this is your right hand side. So we proved this triple integral over v del dot f vector dv is nothing but 3 by 2. So this has been proved. Right. Now, when you want to go with the left hand side, here you have the surfaces. As I told you very clearly, you can see this picture. This picture has got 6 surfaces: S1, S2, S3, S4, S5 and S6. And also I have drawn, so you can clearly see here in, I'm sorry, you can see here in xy plane, you know, of course, z value is 0, and the parallel to xy plane you have this z value is 1, right? And also in xz plane you have y is 0, and parallel to xz plane you have y is 1, and in yz plane you have x is 0, and parallel to yz plane you have x is 1. So these variations you should know, and what I want to do, all this stuff, this information, I will be marking it for each surfaces. For example, if you take S1, I will write z equal to 0 in xy plane, it is in xy plane, so z equal to 0, and of course when z equal to 0, your dz will also be 0. Okay, when z equal to 1, your dz will also be 0 here. Okay, 0, and when y equal to 0, dy is 0, and y equal to 1, dy is 0 again, and x equal to 0, dx is 0, and x equal to 1 is dx is 0. So this information you should know. So I will be writing all this information for S1, and of course the very important thing is n cap, which is minus k vector. Now we will go with the left hand side. Double integral is f dot n cap ds. This is the surface integral. So we have got 6 surfaces in the cube. So we have just added S1 f dot n cap ds with S1. The same way f dot n cap ds with S2 and S3, S4, S5, S6. So we just added all the double integrals with respect to their surfaces. Now let us take S1. In S1 you can see very well here the S1 is nothing but xy plane. In xy plane, you know, z is 0, therefore dz is 0. And of course the unit outward or normal n cap is minus k vector, because it is going inside xy plane, that means inner side, so it is minus k vector. So when you take dot product with n cap, so that is minus k vector here. So f dot n cap is just f dot n cap is minus k here, and of course your xy plane you have xy ds is dx dy. Similarly, when you take parallel to xy plane in S2, only changes your n cap. N cap is nothing but the unit outward or normal, which is going outer side. So I mean that is the top side. So you have n cap is k vector, and z is of course the height. So here 0 to 1. So dv is, the height is 1, but still dz is 0 because differentiation of z, when constant is 0, so it's going to be 0. So dz is 0. So xy plane it is minus k, and parallel to xy plane is plus k. So that is the n vector, like I mean n cap, which is the f dot n cap evaluations, you need to understand that, right? And when you go with S3 plane, that is xz plane, here your n cap is minus g, and in xz plane y is 0, therefore dy is 0. So when you take f dot n cap, so you just substitute minus g here, we will be taking dot product with this f vector, and of course your ds is dx dz. Similarly, when you go with parallel to xz plane, that is s4, you have n cap is plus j vector because it is unit outward or normal which is in the outer side, and of course your y variation 0, here it is the height of the cube, so I mean the elongation here it is y equal to 1, therefore dy equal to 0. You take the dot product of n cap, which is going to be j vector substituted here, so we'll be taking f dot n cap in this way. And when you get into y z plane, your n cap is minus I vector because the corresponding variable x is missing, so x vector is nothing but your I vector, but here it is the inward side, so it is n cap is minus I vector, and here in y z plane x is 0, therefore dx is 0. Therefore when you take this f dot n cap, just your n cap is replaced by minus I here, and f vector is same for all the surfaces. Similarly, when you get into parallel to yz plane, your n cap is I vector because it is drawn outward. I mean the unit outward or normal is drawn outward, so it is I vector. And in parallel to yz plane, of course the elongation from x equal to 0 to x equal to 1 here, but still dx is 0. So we have n cap is I vector. So you just take dot product, and of course in yz plane you have ds is dy dz. The same way here also it is dy dz. So you have 6 double integrals which has to be evaluated. Now I'll do one thing. Let me just go with taking the dot product here. You can see before showing that. See here, these two will not come because only k dot k you have to take dot product. So you'll get the answer will be minus yz. And when you get into s2, again these two will not come. So when you take dot product, the answer will be plus yz. And when you go with minus j, again these two will not come, so j dot j becomes 1, so you have minus y square into minus 1, which is going to be plus y square. Okay, and here again these two will not come, so you have j dot j is 1, so minus y square into 1 becomes minus y square. And when you get into s5, it is j and k won't come, so you have I dot I becomes 1, so you have 4xz into minus 1 becomes minus 4 xz. Again here you have only I dot I, that is 1, so you get 4xz into 1 becomes plus 4xz. So these are the resultant values which will be taken and written in the next step. So all these things I wrote it here, you can see. Now when you substitute z equal to 0 here, this integral becomes 0, and when you substitute z equal to 1 here, this integral becomes y. And when you substitute y equal to 0 here, this integral becomes 0, and when you substitute y equal to 1 here, this integral becomes minus 1 square, which is minus 1. And when you substitute x equal to 0 here, this integral becomes 0, and when you substitute x equal to 1 here, this integral becomes 4z. So all these changes you have to make because in each plane you have one variable will be 0 and the other one, I mean parallel, will be the height of that is 1 or whatever number. Here it is 1, right? So I have just substituted. You can see clearly this s1, s3, s5 gets vanished because all are zeros, and s2, s4, s6 you have some integration parts, so that we are going to do here. So we have s2, s4 and s6. So here we are going to integrate, and of course s2 is nothing but your xy plane, so you have the limits 0 to 1 because all the limits of x, y, z are given in the question 0 to 1. So 0 to 1, 0 to 1, and of course in xz plane again you have the limits are 0 to 1, and I took this minus outside here. And of course in yz plane the limits are 0 to 1 for y and z, right? So the limits are discussed here. Now what we're going to do is, like, we need to integrate this. So y dx, the integration is yx. So I apply the upper limit for x, which is y, and again you get, and lower limit is of course 0. So y dy, again you need to integrate y integration is y square by 2 between the limit 0 and 1. Apply 1 here, so you get 1 square is 1 by 2, lower limit is 0. So this part I have done. Okay, and I'll go with the second integral, dx dz. Just integrate dx, which is x limits are 0 to 1, so apply that, so it is just 1 into dz. Of course dz integration is z, again 0 to 1 limit, so it is just 1. So we have minus outside, so it is minus 1. And the third integral, when you integrate that, 4z into dy is 4zy. Limits are 0 to 1, so you apply for y, that is 4z. 4z integration is 4z square by 2, so which is 4 into 1 square. When I apply the limits, that is 4 by 2. So here the lower limits are 0, so need not bother about that. So that is getting vanished automatically. So I just apply the upper limits. So I got the answers here. So what are the answers I have? I have half, minus 1 and 4 by 2. I just add that. Half minus 1 plus 4 by 2 is nothing but 2. So here you get half plus 1, which is 3 by 2. So we just proved this double integral over is f dot n cap ds is 3 by 2, and which is nothing but your triple integral over v del dot f vector dv, which has been proved earlier. So this proves the Gauss divergence theorem. Thank you.